Hi everyone, this is your lesson on the second half on the binomial distribution. You'll remember we started this before exams, and the slide that you see up is the binomial probability formula that we had talked about. You'll remember, hopefully, we talked about all these little parts of it. We had run through some sample problems, and you also had some homework assigned out of that first half that I will remind you of at the end of this lesson for you. What we're going to do today is complete the lesson on the binomial distribution. We'll talk a lot about how you can use your calculator to make the calculation simple and to basically let the calculator do the work for you. We'll also talk about the mean and standard deviation of the binomial distribution. So to kind of recap, we had run through example 8.5 out of our textbook, you might remember. So this is one that I don't think we had gotten to talk about. So suppose we wanted to find the probability of getting one head in 3 flips of a coin. So we could start out and kind of do it with the tree diagram to determine the answer. That's kind of the old way we had done it. First flip of the coin, you can either get a head or a tail on that first flip. All right, so that would be like flip 1. Okay. Second flip, obviously you could get a head or a tail there. That's your second flip. And then third flip, so that's your third flip. So as we talked about back when we did tree diagrams, all of these branches are laying out all the different possibilities as to what can happen when you flip a coin 3 times. So that first top branch, you could get a head, head, head. You could get a head, head, tail, head, tail, head. So they represent like all the different orderings, if you will. All right, so if we take a look at the ones that had just one head in them, if we start, tracing along the branches, we got one right here, so like this one right here. All right, that's one possibility. Here's another one. And here's yet a third one. So if we wanted to figure out the probability of just getting one head in 3 flips of a coin, 3 out of the 8 will yield that. All right, so our answer should be 3/8. But let's talk about it in regard to the binomial probability distribution, because this is a binomial scenario if you think about it. If you think back to the criteria, the 4 criteria we talked about that at the beginning of the last lesson. If we refer to a success as getting ahead, obviously the probability of getting ahead would be 0.5. So we have our little p-value, our probability of success. There are a set number of trials because we're flipping the coin 3 times, and those trials are independent of each other. Each time you flip a coin, it does not matter what you got on the previous flip. So let's talk about it now, how you would do it with the binomial probability formula. So if we define our random variable x to getting ahead when we flip a coin, because we need to remember to define what our random variable is. So what we're trying to find is the probability that we just get one head. So that's how we denote it in probability notation. So if you think back to how the binomial probability distribution formula goes, out of 3 flips of the coin, we want to obtain one head, so that's 3 choose 1. Remember, the next thing we have is our probability of success. And there's really only one success that we want to have because one flip of the coin will yield a head, and then we multiply that with our probability of failure, remember. All right, so we talked about how we could do that on your calculator. So let's kind of go review that. right, so remember in parentheses, you'll do the 3 choose 1 first, so that's 3. The choose function is under math and across the top to probability, and you'll see it's the third one down there. So it looks like that. Times 0.5, and that's just to the first, so you don't have to bother exponentiating that. Then times 0.5 squared. And if you notice, 0.375 is equivalent to 3/8 that we obtained. All right, so just kind of a great example for you of how, something we did back in the early units of our year with a tree diagram, you now can use the probability distribution formula to obtain. All right, so that's kind of a little recap of what we were doing. So we had already worked through example, this number 8.9. You should have that in your notes and on your handout. And we did 8.11. So if you think back to all those that we had done before, what those were specifically were what we refer to as a probability distribution function. They assigned a probability to each individual value of x. And if you take a look back, for most of the problems, what we were trying to find was something like, probability x equals 1, for instance. What was the probability we obtained 1 head? What was the one with the type O with the kids? I think you were having 5 kids and you wanted to know what was the probability 3 of them would have blood type O. So that was the probability that x equals 3, and x was the random variable of having a child with blood type O. Basically, you'll notice all these have equal signs in them. All right, that's an easy way to know that you have a probability distribution function. Okay, so we're going to talk next about a different type. And we're going to take a look at, start with example 8.7 out of your textbook if you happen to have that handy. It's on page 520, and this is going to segue into another type of distribution function called a cumulative distribution function, and then we'll be talking about the features on your calculator. So I think we talked about one similar to this. This is the one about the engineer who's selecting a simple random sample of 10 switches from a large shipment for detailed inspection. 10% of the switches fail to meet specifications, and we want the probability that no more than 1 of the 10 switches in the sample fail inspection. All right, so if we were to walk through this start to finish, all right, we'd have to first define our random variable. All right, and if you read on, it kind of does tell you. X would be the number of bad switches. Out of the 10. All right, and what we're trying to find is what is the probability that no more than 1 of the 10 fail inspection. So what we're trying to find in terms of our probability notation is that no more than 1. So that would be x less than or equal to 1. So you have a few different ways to do it. So let's kind of talk about how we would have done it, as of last week. If we want the probability that x is less than or equal to 1, well, if that's the distribution we're talking about, it's possible that x equals 0, meaning there are no bad switches out of the 10. But to that, you then have to add the probability that there is just 1. Right? And since we want x less than or equal to 1, we're not going to go any higher than 1. From here, we could really just apply our probability distribution formula. All right, so maybe I'll color code these for you. All right, so let's do this one first in blue. So that's going to be out of the 10 switches, we want none of them to fail. Probability of success. Now remember, a success is getting a bad switch in this case. Little p was given to be 0.1. So we would have 0.1 raised to the 0 power. So if your probability of success is 0.1, your probability of failure would be 0.9, and that's going to be raised to the 10th. Remember, you'd subtract those numbers in the choose function to get that. All right, so that's the first part. Now we have to do probability that x equals 1. Let's do that in green. Ooh, lime green. So out of the 10 now, we want 1 switch to be bad times the probability of success. That would be 0.1 raised to the first, because only we have 1 success in this case, times 0.9 raised to the 9th. So again, that's something you can just do in your calculator, using just as we had done the last example. When you do all that out, it should come out as approximately 0.736. So if you think about what that means is, okay, so this engineer is choosing a simple random sample of 10 switches to inspect. The chances that no more than 1 is bad is a little bit over 73%, which isn't too horrible, I guess. All right, so if you compare this one to the other ones we did last week, you'll notice that this is like a less than or equal to problem that you're trying to solve. What we refer to that as is a cumulative distribution function. All right, and it's cumulative because you're having to add up different probabilities up to including whatever you want to equal. So like in that one, we did the probability that x equals 0 plus the probability x equals 1. It calculates a probability on a range of values. And it's always up to and including that number you're equaling. That part's important. So what you have are kind of two different problems you're going to come across. You're going to have these probability, the cumulative distribution functions, in which you're trying to solve problems like we just looked at. If it happens to be something like, let me see if I can make one up, probability that x maybe is greater than or equal to 3, I'm just making up numbers. You're going to have to turn that into like a less than or equal to problem. So in this case, it would have to be 1 minus the probability that x is less than or equal to 2. All right, remember you're talking integer values, you know, because you can't have a fractional number or a decimal number of successes. So we are talking whole numbers. So if you want to find the probability that x is greater than or equal to 3, in order to be able to do it eventually on our calculator like we want to do, you need to turn it into somewhat of a less than or equal to problem, all right, because that's how the cumulative distribution function calculates. It's always a less than or equal to problem. If you wanted something, and I'll turn this around just a little bit, suppose it was strictly greater than 3, notice no equal to, that's going to be probability of 1 minus the probability x is less than or equal to 3. So you very much have to have a great handle and understanding on inequalities to do this. If you don't, you might want to review some. I like to put it in terms of like a number line analysis, sort of like a number line. What you're looking for in this first one that I made up for you is, if you think of like a number line, so here's like 1, 2, 3. You're looking for the chances of equaling 3 or higher. All right, so that's why you're going to do, you know, up to and including 2, okay, when you rewrite it. In this one, notice you want strictly greater than 3, so it's like an open circle on 3. So when you rewrite it, you have to include it. All right, so that is something you very much have to have a great understanding of. Basically, we assume you come to this course with that understanding of inequalities, because that is one thing that often students will get stuck on. All right, so let's talk now about how we can do these on our calculator. So you'll want to have your calculator handy. We're actually going to go back to some of the examples we worked last week. to show you how we could have done it on our calculator instead of doing it by hand. We'll also talk about how they would expect to see these out of you on the AP exam in the free response. So if you grab hold of your calculator, and these instructions are on the second page, I believe, of your handout for the lesson. The ones we want are under second vars for distribution. And you have to scroll down pretty far. You might find it easier, instead of scrolling down through the list, hit your up arrow and you can kind of come at it from the back end of the list. Now, depending upon which calculator you have, you'll notice here that it says it's 0 for the Binomial PDF. On the TI-84s with the updated operating system, it's going to be letter A. Okay, so just so you know, on the updated operating system, this is going to be an A instead. Okay. So it depends upon what calculator you have. I know on the TI-83s it says 0. Okay. What Binomial PDF, right, notice it's a P, that stands for probability distribution function. These are the ones that are equal to. All right, so we're talking about probability that x equals a number. And if you take a look at the variables, n of course is how many trials, little p is the probability of success, and k is what you want to equal. And we'll run through these on the calculator. And you'll notice that especially with the updated operating system, it will prompt you for all these. So, if you have the old system, you will have to memorize the order in which you type the numbers in the parentheses. All right, so Binomial PDF is probability distribution function. Where'd it go? Okay. And these are the ones, as I mentioned, that will be probability that x equals a number. Okay, the one right underneath of that, so remember how I was saying on the updated operating system that's an A. On the updated operating system, the other is at B. This is Binomial CDF. That stands for continuous distribution function. These are the ones that are the probability that x is less than or equal to k. All right, and notice how it's always up to and including that number. That part's really important. So it's always a less than or equal to. It's going to equal this number. All right, so that's something you have to keep in mind, and why we've stressed so much about writing out the probability notation, because it really does make a difference here. If you do not write it correctly, you'll be calculating the wrong thing. That's why we've been emphasizing it so much. So let's go back to some of the earlier examples we had worked. Some from last week, and if you have your notes there, maybe you can just flip back to it. We're going to start with example 8.5. This was back on page 517. You might have it reworked in your notes. So this is example 8.5 on page 517. This is the one about the blood type O, you probably remember. So remember, you were having 5 kids and you wanted the probability, what we did back then, we wanted the probability that exactly 2 of the 5 were blood type O. All right, and you might remember that the probability of success in this problem was 0.25. You might see that there in your notes. So what we had done, just to kind of refresh your memories, remember you were having 5 kids. You wanted to know the probability that 2 of them had blood type O. The probability of success, meaning the probability of having blood type O, was 0.25, meaning the probability of failure is 0.75. And that's how we had done it back before. All right, but let's run through it and you can see how you would use the calculator features to do this. So let me switch over to the calculator, and I might lose this writing when I do that, just so you know. All right, so since we're calculating the probability that x equals a number, when we do second vars, This is a binom PDF. Oop, I went too far. All right, so if you have the new operating system, this is what you'd be looking at. Or if you're able to expand and give the hints from the TI-83 with that catalog help, you will be prompted for these. So the number of trials was 5 because we were going to have 5 kids. P, little p, that's your probability of success. The X value is, in this case, how many kids do you want to have blood type 0? So it's 2. How many successes? That's really what the X value is talking about. All right, and when you do paste, all right, you'll notice what it looks like. It will bring you up to your main screen, and it looks like binom PDF, and in parentheses you'll notice 5.25 and 2. Those of you with the old operating system, this is the order that you would have to memorize, how you type everything in. So just hit enter, and if you check your notes from last week, you'll notice this is the exact same answer we got by calculating it directly from the formula. All right, so let's try another one. Let's do the one with the that we started with today, the tree diagram. Remember, we were going to flip a coin 3 times, and we wanted the probability of getting 1 head out of those flips. We could do that here. All right, remember that answer was 3/8, 0.375, if you check your notes from a little bit ago. All right, so since we want the probability that x equals 1, right, that's a binom PDF for probability distribution function. All right, so we were flipping a coin 3 times, so change the number of trials to 3. Little p, of course, would be 0.5 because there's a 50% chance of getting a head. Remember, we wanted to only get 1 head when we flip the coin. All right, so do end paste and then enter, and there's the 0.375 we got. This is great for multiple choice questions. Saves you a lot of time and writing. On the free response, basically what they are going to look for is exactly what we've been talking about. They want to see the probability notation. They generally do want to see the setup of the binomial formula, like the n choose k, then times little p raised to the number of successes, then times the probability of failure raised to n minus k. They generally do want to see that. This is a great way to check your answers and still do the calculations. You know, it's a little bit less typing. But on the multiple choice, that's where I think you're really going to find this handy. All right, so let's take a look at 8.9. That's another one we had done last week. It's number 8.9 on page 519. So let's kind of go back and we can sort of reset up what it had looked like. So this is towards the end of class the other day. This is 8.9 on page 519. Again, if you're able to find it in your notes, you might find it helpful. This is the one that it was still the number of, you know, having 5 kids and how many kids are going to have blood type O. We wanted, in this case, we wanted to find the probability that at least one of the kids were blood type O. So if remember how we had expressed that as x greater than or equal to 1. So the way we had done it, and I believe this is exactly how we did it last week, we rewrote it as probability, or 1 minus the probability that x equals 0. Well, this is something, this part right here, you could do on your calculator if you wanted to. So then you'd have 1 minus that, you know, and you'll get the same answer we did before. So this is really just giving you different options, you know, kind of saves you a little bit of typing. It's great on the multiple choice questions. For a lot of these, they are going, especially the equal to problems, they are going to want to see the setup of that binomial distribution formula. Let's take a look at, let's see, See if we can find a CDF one. Example 8.7, the one we just took a look at, the one about the switches. Let's take a look at that one again. All right, if you think back, this is the one where the engineer was going to do a simple random sample of 10 switches. And remember, we wanted to find the probability that no more than one switch was bad. So we had expressed that as the probability that x was less than or equal to 1. This is something we could do right on the calculator. Now, on the free response, and this is where you kind of just have to know what the expectations are. Equal to problems like this, they're going to want to see the formula. Problems with a cumulative distribution function, so long as you show the probability notation, as you see here, they're completely fine with you just doing it in your calculator. So it really is a matter of, you have to keep in mind what do they want when. As we've mentioned before, the AP exam, it's like a game and you just got to know their rules. So, but this is one you easily could do on your calculator, and I would definitely encourage that because it saves you a lot of time. So let's take a look at that one. All right, so we'll do second vars. Now, since this is a less than or equal to problem, remember this is a binomial CDF problem for cumulative distribution function. All right, you do need to remember which one you need to use when. All right, PDF is for the equal to problems, CDF is for the less than or equal to problems, and they have to be a less than or equal to problem. If it's not, you have to rewrite it before you do it. All right, so remember, number of trials were 10 because there were 10 switches he was going to pull for his sample. Remember that 10% of them were known to be bad. And we wanted no more than one. All right, remember that X value, it's the maximum number of successes. It's always up to and including that number. All right, remember the answer had been 0.736 when we did it before. And there you go. So I think especially on the CDF problems, the less than or equal to problems, this can really save you a lot of time. All right, so we'll look at another example together. This is the next one we're going to look at. It's number 8.15. It's on page 524. Guessing on a multiple choice quiz. There you go. So suppose that Erin guesses on each question of a multiple choice question. Now we're only doing part A, just so you know. So if each question has 4 different choices, find the probability that Erin gets 1 or more correct in a 10-item quiz. All right, so remember the very first thing we'd have to set down is what our random variable is. All right, you can't go throwing around x's without stating what they are. All right, so assuming we're going to use x as our random variable, remember it basically states what it is you're looking to see happen. In this case, we want to know how many answers Erin's going to get right. So it's like the number of answers correct or something like that. All right, so if we just lay out what we know, it's a 10-question quiz. So our number of trials, this is our number of trials, would be 10. And it's each question is 4 different choices. So you have to think about what your probability of success is. Because if there's 4 different choices and you're choosing one, probability of success is 0.25. So this is our probability of success. All right, so what it is we're trying to find in this case, and we are going to do it with our calculator eventually, we want to find the probability that Erin gets 1 or more correct on the 10-item quiz. So we want the probability that she's getting at least 1 right. All right, now remember, if we are going to use our calculator, calculator won't do greater than or equal to problems. We have to rewrite it. So we need to think about how to rewrite it. It's always going to be 1 minus something. So if you think of, again, I don't know if the number line analogy works for everybody. I'm not sure. But here would be none, because I guess it's possible Erin gets none right, so we got to include 0, I suppose. Okay, so we want the probability that x is greater than or equal to 1. So it's like a filled in circle on 1. Then you're going this way. So in terms of 1 minus, you got to do probability that x equals 0. All right, so if we wanted to practice setting it up in the binomial probability formula, so out of the 10 questions, we're talking about her getting none right. All right, so that would be 10 choose 0. Probability of success is 0.25, and she's not getting any right, so that's raised to the 0 power. So probability of failure is 0.75. So this is something you easily could just do in your calculator. Another thing we could do is just kind of do that probability PDF, because it isn't x equals 0. And then we can just get that answer and do 1 minus it. Okay, so let's go take a look at that. All right, so we're going to use Binomial PDF. We had a 10 question quiz, so n equaled 10. P, probability of success, was 0.25. We were talking about the probability that x equaled 0 we wanted. All right, so hopefully everybody's getting that 0.056, but then we have to do 1 minus it. So 1 minus, you can copy and paste, just use your up arrow, hit enter. And you'll notice it kind of just copies and pastes it. That might only work on the new operating system. The old operating system might not do that. You can do second enter if you have the old operating system to bring up that whole decimal. And your answer is 0.943. So if you think about what that means in like real life, okay, Erin's taken this 10 question quiz. The question was, what was the probability that she gets 1 or more right if she's just randomly guessing? Okay, she didn't study, and she's going to guess on everything. So she's got like a 94% chance of getting at least 1 right out of the 10. But maybe it's only 1 right she gets, so that wouldn't be a good thing. All right. So the homework you're going to have out of this, we got one more little part to cover. The homework is really designed to give you practice setting these up, especially working on the probability notation, stating what your random variables are. There are a lot of things you definitely need to pay attention to as you do your homework if you're going to master this. Okay, so please take the care to do that. All right, you want to be stating what your random variable x stands for. You know, what is it you're trying to find in terms of the probability notation. I encourage you to practice doing it on the calculator because you definitely want to get adept at doing that. So the homework, it's going to look like a lot of problems, but quite frankly, they go pretty quick because they're pretty short. I've already done them all. All right, so let's go back and finish up the lesson. There's really just one part left. All right, and that's talking about mean and standard deviation of a binomial random variable. All right, you'll remember from the last unit, Unit 4, we talked about mean and standard deviations for random variables. You'll remember that from the end of the unit, hopefully. We're still, in terms of our variables that we're defining, all right, we're still defining P as the probability of success. And we do have a probability of failure as well. So if we know we have a random variable that is a binomial, that it has a binomial distribution, n is still the number of trials, the number of observations. The formulas are pretty short. There's just 2 of them. The mean of the binomial random variable is just n times p. Very easy. And you might remember from Unit 4, one thing that we talked about in terms of the standard deviation is the need to go through the variance. That was for a normal distribution. Binomial distribution, you don't have to do that. So that's one difference that you're going to have to keep in your head. Those rules we did back in Unit 4, they were for a normal distribution. This is a binomial distribution, so it is different. So therefore different rules. These are rules given to you on the AP formula sheet. You might remember as we went over it, I said we stopped at a certain point, and the ones after that were from the next unit. These were on there. So at least they're pretty short. Another way to rewrite this last one, a lot of people like to think of it as N times P, so the number of trials times the probability of success times the probability of failure. All right, a lot of people call Q the probability of failure. You'll often see textbooks do that. All right, but the big thing to remember is this last one. These are only for the binomial distribution. If it's a normal distribution, you cannot use these. So very, very, very simple formulas. Much easier, I think, than the ones we did for a normal distribution. You might remember that long variance one. That's the one you had to do each observation minus the mean you had calculated. Square that whole quantity, then times by the probability. So you might remember it was that long drawn out formula. This is very, very, very simple. So we'll look at a couple examples and then we'll be done for that. All right, so let's start with number 8.22. This is on page 529. And you'll see how short they are. So this one's talking about Mark McGwire's home runs. Hopefully you know who he is. In 1998, Mark McGwire, he played for the St. Louis Cardinals, baseball. Hit 70 home runs, which at the time was a new major league record. And the question was this feat as surprising as most of us thought? In the 3 seasons before 1998, McGwire hit a home run in 11.6% of his times at bat. He went to bat 509 times in 1998. And his home run count in 509 times at bat, they're telling you it has approximately a binomial distribution. They tell us that n equals 509 because that's how many at-bats he had. So n equals 509. And the probability of success, remember it said he hit a home run in 11.6% of his times at bat. So that would be 0.116. All right, and what they're asking us is what is the mean number of home runs he will hit in 509 times at bat. And we're just going to do that part of it. Okay, we're going to ignore the last sentence. So we want what is the mean number of the home runs that he would hit in 509 times at bat. All right, so we have to define our random variable, assuming we call it x. So that would be how many home runs he hits. All right, and we're trying to find the mean of that random variable. So remember what the formula is, just n times p. Really easy. So just multiply them together. You get 59.044 home runs. So if you think about it, remember they had said in 1998, which was when this data was from, he had hit 70, which was the home run record at the time. But statistically, based upon his previous, year's performance, we would have expected, remember we often refer to the mean as the expected value. So really, if he were to have 509 at-bats, you know, we would have expected him to have only about 59 home runs. All right, but what he actually hit was 70. So, yeah, it kind of was surprising, you know, because he's definitely over what the expected number would have been. So it was sort of surprising. A good surprise. Until the whole steroid thing came out, and then the record was abolished. So that's another issue. All right, so let's take a look at another one. The next one is 8.23, and we're just going to do parts A, B, and C. And it's on the same page. I guess 530, because you had to flip the page. So this is about an opinion poll done locally, and it says that many local polls of public opinion use sample sizes of about 400 to 800 people. So suppose 400 adults in Richmond were asked the question, do you approve of President George Bush's response to the World Trade Center terrorist attacks on September 2011? So suppose we knew Bush's approval rating on the issue nationally was 92% a week after the incident. All right, so the first thing they're asking us to do is to determine if the random variable, like what is the random variable? They're asking us to define it. And then also, is it a binomial random variable? So we'll go through those four criteria again. All right, well, we're talking about his approval rating and how many people approve of Bush's response to 9/11. So maybe we can just call X to be just approve, I guess. All right, so now we have to go through the criteria in order to be binomial. All right, remember there were 4 of them. All right, the first one, remember, is that you had to be able to identify a success. All right, so in this case, a success is identified as approving of Bush's response, a person approving of his response. And then obviously a failure would be not approving it, okay? Remember, second criteria is you have to have a set number of trials. So in this case, we're talking about 400 people in Richmond had been polled. The third issue addresses the independence. So if you think you're doing, you know, consider you're doing an opinion poll with 400 people, it should be true that one person's response is independent of another. And finally, the fourth thing is you need to be able to identify your probability of success. Now remember, it said nationally he had a 92% approval rating, so we can use 0.92 for that probability of success. So since it met all the criteria, basically X is a binomial variable. Right, so that kind of also reviews some of the stuff we did last week. All right, so if you take a look at part B, calculate the binomial probability that at most 358 of the 400 adults answered yes to the question. All right, so if you lay out what we want to find the probability, and it says that at most 358 of the adults answered yes. So X would be less than or equal to 358. All right, so we've already established this is a binomial distribution. The fact that this is a less than or equal to probability we're trying to find, we can do that in our calculator using the binom PDF, or CDF rather, sorry. All right, so why don't you give that a try? All right, I'm going to stay on the screen while you try it. So you'll do second vars, do binom CDF for cumulative distribution function. Number of trials would be 400. Little p is that 0.92. Our x value is 358. All right, remember, they're always less than or equal to problems. All right, so I'll give you a second to do it. It's not that big. It's coming out about 0.044. So if you think about what it means, real life, there's only like a 4.4% chance that at most 358 adults out of the 400 polled would answer yes to approving of his actions. All right, letter C then, find the expected number of people in the sample who indicate approval. Now remember we talked about, keywords to look for. They ask us for the expected number of people. Remember that means expected value. They want the mean. So we're talking specifically about the mean of this random variable x. Remember that's the one, easy, nice little rule, n times p. So n is 400. Probability of success is 0.92. And if you think about it, it kind of makes sense because if we're trying to figure, okay, we're polling 400 people, we know the national approval rating is 92%. So if we want an estimate as to how many we might expect to approve of Bush's actions out of the 400, it kind of, hopefully it makes sense to you that why we're doing 400 times 0.92, right? And that's really just where the rule comes from. So if you do that, you should be coming up with 368 people. And they also ask us for the standard deviation. All right, so this is that one where it's the square root. And I'm going to write it as n times p times q. So big square root, n is 400. P is 0.92, and if our probability of success is 92%, obviously 8% are not approving of his actions. Just when you type that in, make sure you're doing the square root of all those multiplied together. Just watch your parentheses or whatever. And you should be getting 5.426, I guess. Or 4.3 if you just round there, that's fine. So remember what that tells us. The standard deviation is sort of the average distance from the mean. Sometimes some people will think of this as almost like a margin of error in terms of how far off you could be. Some people interpret it that way, but we do refer to it as the standard deviation. All right, so you can see these problems are really short when it comes to the mean and standard deviation. All right, so let's recap what your homework's going to be. All of this is due Tuesday, January 22nd when we return to school. After, I know a lot of you have off Friday, then of course on the 21st in honor of Martin Luther King. The first half of the homework that was assigned last week, maybe you've already done it, is those problems 8.2 up through and including 8.12 that you see there. Again, you might have already done those perhaps last weekend maybe. From this second half, you can see at the bottom that starting at number 8.14, I'm going up to 8.40. You'll notice several of those you're only doing certain parts, so please do take note of that. All right, I'll leave this slide up for a minute before I close out the lesson. Hopefully it was helpful to you. I think it was an okay one to have to kind of walk through with me not there in person. So I shall see you on the 22nd, and we'll recap all of these. We're also going to do a kind of a closing activity regarding the binomial distribution, and then we'll start lesson 5.2 on Wednesday. Okay, so see you then. Make sure you get your homework done. This is counting as 2 homework assignments, so please do make sure you're doing both. Okay, you don't want to start off the new semester in the hole and already using your homework passes. So please do make sure you get it done. All right, and I'll see you next Wednesday.